Welcome back to our course on GPS. We're just starting on Module 1, trying to give you a little bit of a feeling for what is GPS, why do we care about it so deeply, and how are we going to organize the course. Here's an outline of our first 5 snippets. Professor Van Diggelen has already talked to you about the overall outline of the course, and he nicely organized that around the various functions that GPS performs, both to operate nominally and to provide better accuracy, better sensitivity, and so forth. Today, I'll talk a little bit about my view about how GPS works. Once again, just a very quick snippet to give you a feeling, and then give you my feelings about why GPS is so important. So that will be Module 1.2. Frank will come back, talk about the simplicity and beauty of GPS in Module 1.3. And then I'll come back and talk about how this course will be structured in terms of the outline and the prerequisites that we require for this course. This really is a course that's best suited for people who have a strong undergraduate exposure to technical matters. And then finally, module or snippet 1.5 will give the actual course schedule and talk about some specific things like the laboratories that we're eager to expose you to, the books that are available, the chat site that's available, and so forth. So with that, let's hop ahead. As I mentioned, Professor Van Diggelen has already given you a course outlined by function. I'll talk a little bit about my view of the how and why of GPS, and it begins with this picture. So here are all the essential elements of GPS. There are some 30 satellites up there today from the GPS system, the US system, and there are an additional 30 satellites or so from Russia and Europe put together, and then an additional 15, 16 satellites from China, and then a few others from Japan and India. So all told, we're pushing 80 satellites or so. But what we show here in the upper right, the red clock, is a single satellite. So we're just taking a single satellite perspective here. And we need that satellite to broadcast a radio signal at a known transmission time. That's element number 1. And for that transmission time, we also must know the location of the satellite. After all, we're going to calculate ranges from the satellite, the red clock, down to the user, the green clock, and for those ranges to have meaning in a reference frame that works well for the user, we also have to know where the satellite is in that user frame, in that reference frame. Element number 3 is the radio wave propagating from the satellite to the user. That's element number 3. We need that to be reasonably close to the speed of light. A few perturbations relative to the speed of light are fine. We model those, or we have techniques to remove them, but we do count on it being reasonably close. And then finally, element number 4, in terms of this one satellite to user description of GPS, is the measurement of the time of arrival by the user. And that's the green clock down there on the left. So with those 4 elements, we can develop the pseudo-range equation, which is shown in the gray box. And I won't take you through all of it right now, but I ask you to become increasingly familiar with it as the modules progress. And we'll go through it term by term. The key thing there in the equation tau and the supporting equation d is that within lie what we call the estimanda, and that is the xu, yu, zu, and xu, yu, zu describe the location of the user. And we would like to solve for that. In addition, in the top equation, you see bu. And bu is the clock offset of the user clock relative to GPS system time. So all the satellites shown, let's say, in red, are synchronized to each other. So they share a common time base. But the green clock, the user clock, is by design, by necessity, inexpensive. So we have to solve for the clock offset between green and red. So in fact, we have 4 things that we have to solve for: bu, xu, yu, zu. The rest of those variables in the gray box we hope are either reliably provided or something that we can estimate based on auxiliary information available to the user. So that's the overall picture of how GPS works. And please know that you have to repeat that green to red link for some 4 or 5 satellites in view. The 4 or 5 makes sense because we're solving for the 4 unknowns, X, U, Y, U, Z, U, B, U. So, in a nutshell, that's how GPS works. Why do I care about it so deeply? I am, in my heart, an environmentalist. And in 1989, any doubt I had about working on navigation or not was wiped out when the Exxon Valdez ran aground in Williams Sound in Alaska and spilled 11 million gallons of oil into the Prince William Sound. This was just a terrible event for the environment of Alaska, and the after effects are still felt today, some 25 years later. So that's, I'm a navigator, I'm a navigation engineer. The other great care I have has to do with the navigation of airplanes. And here we show an airplane traveling up the Gastineau Channel. The Gastineau Channel leads from the Seattle direction up to the city of Juneau, Alaska. And Juneau is shown there in the upper left. I'll highlight it here for you so you can see it. It's right there. And the airplane is traveling up the Gastineau Channel, which it would like to do because the alternate route into Juneau goes around this island here. And to follow that route requires quite a bit more fuel and quite a bit more time and makes you more sensitive to inclement weather. Well, in Alaska, inclement weather is a fact of life, so it's nice if you can come up with a navigation system that allows you to fly down this narrow channel. By the way, the height of these mountains on the side is on the order of 5,000 feet, and this drawing is to scale. That height is, in fact, a reasonable fraction of the width of the entire channel. So it's a very narrow channel, and if the weather is such that the clouds are down to 1,000 feet or 500 feet, this channel was impassable before GPS. But today, people fly into Juneau, Alaska, many flights a day based on GPS guidance down this narrow channel, even when it's packed with fog and clouds. So that's another core part of my care about GPS, and I hope it's one that you get excited about. I'll mention it going forward in this course, but please know it's a very narrow application area for GPS, and Professor Van Diggelen will expose you to GPS applications that are based simply on your smartphone and are there for all kinds of very much everyday applications, and not quite as demanding as navigating ships at sea or airplanes down narrow channels. One final look ahead that's close to my heart is when we use GPS for safety critical applications like those two I just mentioned, it's important to monitor it and make sure that everything about GPS is going properly. Like any complicated system, it does have glitches, bugs every once in a while. They are extremely rare, on the order of once a year. Even so, if we're landing airplanes or guiding ships using GPS, we do monitor it independently, and that's what you see over here on the left. These two antennas are looking at the same GPS satellite signals as the approaching aircraft, and if any corrections are required or any warnings are required, the master station on the ground uses these signals to figure out what those warnings and corrections are and broadcasts them up to the aircraft. This concept is called differential GPS. It targets the improvement in the accuracy of GPS from, let's say, around 10 meters down to around 1 meter. And it appears in multiple guises. Multiple versions of this are in the commercial community today. They're used for aviation, for maritime navigation, for energy survey, and any application where you want to get down to 1 meter accuracy or better. So that kind of architecture will show up several times in this course. So thank you for your attention on this introductory snippet. Next, Professor Van Diggelen will come back to you and talk about his feeling about why GPS is so deep and beautiful. Thank you.